Hello everyone, welcome back to the NPTEL course on materials informatics. Today's lecture will be a continuation of the previous lecture where we looked at ensemble models. So the wisdom of the crowd and how random forests are a very powerful set of ensemble models built upon decision trees, right. And we also touched upon sequential learning, right, as a way to build ensemble models which are more robust compared to simultaneous learning models, which is the classic random forest, right. So let us now get started. So just as a recap, so we looked at sequential learning, we started touching upon sequential learning where we train models in a sequential fashion compared to a classic random forest where we take or train all the weak models at once. And there are two popular ways of doing sequentially learned ensemble models. One is called as AdaBoost or adaptive boosting, other is referred to as gradient boosting, right. Let us now look at AdaBoost and gradient boosting. So in the case of AdaBoost, so what the model tries to do, what the ensemble tries to do is that each individual models, they try to reduce errors on instances that were actually not fit very well, that were underfit by the predecessor. So let us take an example here, right. So let us say you start off with this collection of data points here, you create one weak model here which sort of creates a prediction that looks like this, right. We now see that there is this one instance or one data point where the weak model has a fairly large error, right. So we then pass this pass this information to the next model which basically tries to ensure that this data point is predicted more accurately, right, compared to the remaining data points. So it now tries to correct this model and has a newer prediction that sort of looks like this, right. So the newer prediction is sort of corrects the older problematic data point, but then it creates 3 new data points here which are now badly predicted, right. So we then send this information to the next weak learning model, so where these 3 data points are identified as underfit. Now the new model tries to make predictions or make corrections such that these 3 data points are also corrected compared to the previous iteration. Now you see that compared to the first model, the third model, so this is the second model is worse compared to the first model, but the third model is comparatively much better compared to the first model, right. So the error on this data point is lower than the first model. Of course you create new outliers, but then overall the model seems to get better, right, as you keep reducing the errors on the outliers, right. So this is how adaptive boosting or AdaBoost sort of works. So in general for the final prediction, right, so let us say you create a bunch of trees like this, right. So for each decision tree you can actually, or each weak model in general, you can actually create or calculate the amount of errors being made. So you can calculate the mean squared error for this model, you can calculate the mean squared error for this model, mean squared error for this model and so on. So when you take the final weighted aggregate, right, trees or models with lower errors, right, across all the data points, they generally have higher weights in the final prediction, right. So when it comes to a regression model, they have higher weights, and when it comes to classification model, they have higher weights in the final classification as well, right. So the way to sort of create AdaBoost models is through the ensemble module itself. You can create an instance of the classification model or the instance of the regression model, right. So both are possible with AdaBoost. So that was AdaBoost, which is one example of sequential learning. The other way to other popular way to do sequential learning is referred to as gradient boosting. So what happens here, right. So in gradient boosting, so each subsequent model tries to correct the residual errors, so the set of errors that is being made by the previous predictor or the predecessor. So let us take the example of decision trees again, right. So let us say you are trying to do a regression task here, right. So in the first task your decision tree sort of comes up with this kind of prediction, you see that this is obviously not that great. So for each data point here compared to its prediction, you can actually calculate the residual. So residual is basically the difference between the model's prediction and the true value, right. So for each data point we can actually calculate the residual, and we can actually consider them to be the set of data points that is feeding into the second decision tree, the second model here. So in the second decision tree we have residuals here plotted as a function of your feature here, right. So the second decision tree now tries to reduce the mean square errors on these residuals, right. So that is what it does. So your ensemble now becomes a summation of your first model, your first decision tree here, and your second model which has been trained on minimizing the residuals, right. And you see that the ensemble is now getting better than the initial decision tree, right. So these predictions are much better than the initial predictions, right. You can now repeat this one more time. So in the case of the second model you have certain predictions, right, of the residuals. You can now take the difference in the predictions of this model and the actual residuals themselves. So we basically taken y minus h1x, which was this target value, minus h2 of x, which is the predictions made by this model. So is the difference in the residual of the residual, right. So that is why the model is referred to as gradient boosting, because we are trying to minimize the gradient of the errors, right. So we can now calculate the residuals of the residuals here, and then we can once again try to calculate fit a decision tree model here, and let us say this is the fitted model. We can then include this model's predictions in the ensemble, and we see that now the ensemble becomes even better compared to the previous case, right. So at each step gradient boosting tries to reduce the errors on the residuals made by the previous model. So over a number of steps you try to minimize the gradient in the total amount of errors that you are actually getting in your models, right. So there is one very important hyperparameter that is associated with gradient boosting, that is referred to as learning rates, right. So in the learning rate here basically scales the contribution of each predictor, right. So keep in mind that we are as we go down in the sequential learning, so as we keep increasing the number of decision trees, right, we are trying to reduce the number of errors in the gradients themselves, right. Which implies the models can become quite oscillatory, right, as we go down. So we make some errors on some residuals in model 1, and then when we go to model 2 maybe a subset of data points the residuals are minimized, but another set of data points the residual sort of blows up, right. So we do not want the models to become oscillatory in nature. So learning rates sort of adds in some kind of a damping factor, which ensures that as we keep adding more and more models, the newer models tend to have lower weights in the aggregated prediction compared to the older models, right, which try to make predictions on the actual data set or the first order or second order residuals, right. So the way to sort of implement gradient boosting is once again using the ensemble module. So you can once again do gradient boosting classification tasks as well, or do gradient boosting regression tasks. Okay. Another sort of important idea that is often used in ensemble models is the idea of stacking. So where instead of doing simple aggregation, so in the case of regression, a simple aggregation is just taking the mean value. In the case of classification, a simple aggregation is taking the majority votes, right. So instead of doing simple aggregation, we can also train a specific model that sort of figures out how to add up the predictions or how to aggregate the predictions from individual models. In other words, this final model here can assign different weights to the predictions made by the different models, so that its own final predictions are much better compared to a simple average of these predictions or a simple majority vote of these predictions, right. And the way stacking is done, so if we were to train a separate model to take a weighted average of the individual predictions or a weighted vote of the individual predictions, that is referred to as stacking. And the way stacking is often implemented is via having holdout data sets or validation data sets, right. So we expose individual models to subsets of our training data, and then we train this blending model on a validation data, so that the blending model can stack up its predictions on the individual weaker models, right. Unfortunately, so stacking is quite a popular approach that is used, but unfortunately there is no native implementation in scikit-learn. So we will have to implements stacking as with a separate workflow. So we can use a separate decision tree that takes in predictions from individual decision trees as its own features, and then it's trained on a validation set to make its final predictions, right. So these predictions have to be made separately, the stacking needs to be done separately, and the final prediction needs to be tested separately. So there is no real native implementation in scikit-learn, but using a bunch of decision trees or support vector machines and other tools out there, other models out there, we can always create a stacked model. So with that we sort of come to an end on ensemble models, and we switch gears to dimensionality reduction, which is a very important problem or an important challenge in machine learning machine learning problems or machine learning projects. So one thing to always keep in mind in any machine learning problem is what is referred to as the curse of dimensionality, right. So in general we almost always have to deal with a large number of features, right. So in material science that could be, let us say you are trying to predict formation energies, right. Maybe the features are, what is your crystal structure, what are the elements being present, right, and properties of those elements themselves, where are the atoms sitting, what kind of bond lengths you have, what kind of bond angles do you have, and so on, right. So just to predict a simple formation energy, one target value, you may require or you may have to use hundreds or even thousands of features, right. So a large number of features is almost always inevitable in any machine learning model or machine learning project, and these large number of features often make the model slower to train, and it also makes it harder to find good solutions, right. So in general we want to have large number of features because that can make our models very robust. So if we find a good solution, it will be a truly good solution, but large number of features also makes our models slow to train, right. So we saw that most of the models they become they sort of computationally scale of the order of number of features or number of features squared, number of features cubed, and so on, right. So the models become progressively slower to train, and when you have models that are slower to train with large number of features, it in fact affects our ability to find good solutions, or affects our ability to find the right set of features so that we get the good solutions, right. So this is one sort of thing to keep in mind. So in general we have to almost always deal with large number of features. We want to identify good set of features, but when we have large number of features it becomes difficult to identify good set of features, so right. So that is the curse of dimensionality. The other interesting thing to keep in mind is that things behave very differently in higher dimensions compared to lower dimensions, right. So for example, if you take a simple square, right, and if you calculate how the probability of one point being closer to one of the edges of the square, right, that probability, let us say it is about 0.4, right. If you now do the same, if you calculate the same probability of one point being far away from a cube, so let us say we took square of dimensions 1, now if we just increase the dimensionality, we take a cube of dimension 1, and we want to calculate the probability of any point being close to one of the faces of our cube. So basically one of the boundaries or borders of a cube, the probability will actually increase, right. So if in a square it was I think in a square is about 0.4%, in a cube I think it's about 0.1 sorry, in the square is about 0.04%, I think in a cube is around 0.16% or something like that. So in general the probability that you would find a point close to a border, so close to a face, close to a edge, close to a vertex, goes up when you increase the dimensionality of your problem itself, right. So there are more points that are closer to the border, so a vertex, an edge, a face in a high dimensional hypercube compared to lower dimensional cubes, right. One can also sort of think of this as extrema in sort of data points, right. So let us say you want to classify people, right. So if you just want to classify people as right handed and left handed, maybe that is a very straightforward classification, maybe 60% are right handed, 40% are left handed, right. So you would still find a large number of people that are not extreme. So in the sense that large number of people are still right-handed, large number of people are still left-handed. Now you let us say you create one more axis of classification, and that could be whether they are Indian or non-Indian, right. So among right-handers there will be a fraction of Indians, among left-handers there will be a fraction of Indians, again among right-handers there will be a fraction of non-Indians, among left-handers there will be a fraction of non-Indians. So you now see that there is more fragmentation in the data, right. Now you add one more feature, right. What fractions of Indians are from the north, and what fractions of Indians are from the south, what fractions are vegetarians, what fractions are non-vegetarians, what fractions are coffee lovers, what fractions are tea lovers, right. And it could be, and it could also be what fraction is male, what fraction is female, what fraction is tall, what fraction is short, and so on. So if you create more and more dimensions of classifying people, you will see that the number of people that fall under each subset of classifications is actually fewer and fewer, right. So the more classifications you do, the more the fewer the number of people that actually fit into one specific domain, right. Or in other words, most people become very extreme, right. So if you let us say have a sample size of 100, and let us say you create 100 dimension or 100 ways to classify that sample, right. You may end up in a situation where in each combination of features there is only one data point, right. So in each subset of or each bin there is only one data point, right. And this can also be interpreted as the fact that each data point becomes very extreme, right. So you have so many ways of classifying your data point, and since you have so many ways of classifying, each data point chooses to aggregate to as extreme a position as possible, right, compared to a simpler classification where most data points are fairly close to one another, right. So this is again one problem with respect to high dimensions, right. So whenever we have high dimensions, we have data points that sort of move very close to the extreme situations or move close to the borders of the high dimensional space, high dimensional space. And because this is very common, so because data points tend to move closer to the extremes, closer to the borders of a high dimensional space, the distance between data points actually increases quite dramatically in a high dimensional space. So if you were to have very simpler ways of classifying or very simpler ways of bucketing people, whether they are right-hander or left-hander, whether they are Indian, non-Indian, and so on, the distance between the data points or the data points themselves will form fairly dense clusters compared to if you classify people with 100 different axes, right, 100 different varieties, right. So the distance between data points will actually increase, or the data will tend to spread out more and more as you create more directions to classify or more directions to featureize a data point, right. So the distance actually increases as you keep increasing dimensions, which implies that in a very high dimensional space you will almost always end up with having a very sparse collection of data. Your data will become very sparse. So at any given direction, at any given facet or any given boundary, you only have a few data points, right, and the distance between those data points is very large, which implies you have very sparse distribution of points in your high dimensional space, right. So this is sort of a problem, right, in machine learning. So even if you just have like 100 features, right, I mean in our MNIST data set we use 784 features, right, MNIST classification data set. So even if you have 100 features, right, if you want to create a very dense data set, you may need more number of data points than you have atoms in the universe, right. For you to have like normalized distances between data points that are less than 0.1, right, in a 100 dimensional phase space or feature space. So it is almost impossible to create a dense enough distribution of data points in a very large dimensional space, right, which implies we have to identify the dimensions that are actually important to us or the features that are actually important to us, and this is where dimensionality reduction becomes very important, right. So one example is in the case of the MNIST classification itself, right, we can sort of see that most of the digits that are written are closer to the center of the 28 by 28 pixel image, right, which implies we can actually cut out most of the edge pixels and still be able to do a reasonably good classification, right. So, if we cut out the edge pixels, we are basically reducing the number of features, or we are reducing the dimensionality of our problem, right. So, instead of having 784 features, maybe we only have 300 features, right, and that increases the density of data, and that allows us to find better solutions, right, and also makes our models lighter, right. So, that is the key principle behind dimensionality learning, and there are two popular ways of doing dimensionality reduction. One is through what is referred to as projection, and the other is referred to as manifold learning. Okay. So, what is projection learning? So, in projection learning, we project whatever high dimensional data we have onto some kind of a lower dimensional space, right. The simplest example is from a 3-dimensional space to a 2-dimensional space. So, let us say you have a collection of data points here. So, in a 3-dimensional space, right. So, you have a collection of blue data points here. Now, I can try to draw a hyperplane, right, such that I sort of ensure that no two data points are directly on top of each other, right, when I do projections. So, I will draw a plane here, a 2-dimensional plane here, and I will take projections of individual data points on the plane, right, that is indicated by the black arrows here, and I will try to draw a plane, and if I manage to draw a plane where I ensure that data points are not directly on top of each other, right, then I have created a low dimensional representation of the data points that is still reasonably good enough for me to do either classification or regression tasks, right. So, this is referred to as projection learning, where I try to construct planes or lower dimensional objects, right, whereby I can project my higher dimensional data points such that no two data points cluster or clump onto one another, right. So, if I were to do this task successfully, I may get a plot that looks like this, right. So, initially I had x1, x2, x3 3 features. Now, I have managed to reduce them to 2 features, z2 and z1, and my data points sort of distribute like this, and now I can try to learn from something from this data points, right. So, be it classification or be it regression. And one of the most popular models for doing projection learning is referred to as principal component analysis, or PCA, right. So, how does PCA work? So, it tries to always choose a projection that maximizes variance. So, keep in mind, variance here has a slightly different connotation. It is not the variance of the model itself, which means a tendency of the model to overfit. It is the variance of the data points, right. So, let me give you an example, right. So, let us say I want to project this 2-dimensional data points into a single dimensional vector, right. So, if I were to choose let us say my dashed line here, right. So, this is going to be my vector of choice. So, along this vector I am going to project all of my data points, right. So, if I were to do that, I will get this distribution here, right. So, where I have distribution of singular data points on my vector, and I see that some of the data points are clumping onto one another, they are clustering onto one another, right. If I were to do the same exercise along the dotted line here, right, which has an even more negative slope, right. So, if I were to do a projection on the dotted line here, I will see that my data points tend to cluster even more, because if I were to project all of them onto this singular vector, the distribution of the data points is fairly small, right. But if I were to do it on the solid line here, I see that my data points are distributed over a larger range, right, along my solid line or my solid vector here. So, this distribution of data points within the low dimensional space is what I refer to as variance, right. So, in principal component analysis, the model tries to maximize the variance, right, maximize the variance for the data points that I have in my high dimensional space, right. So, if I were to project this collection of data onto a collection of 2-dimensional data onto a single dimensional vector, I will use this vector of C1 here, right. So, that will be my principal component, right. So, my principal component analysis basically tries to identify these kinds of orthogonal axes that maximize variance. So, the set of axes that maximize your variance are referred to as your principal components. So, let us say you have a 10-dimensional data, 10-dimensional feature space, and you want to reduce it to 5 dimensions, right. So, what principal component analysis does is it tries to identify 5 orthogonal axes that maximize the variance of data, right. And those 5 components are referred to as principal components, right. and in general the collection of these principal components will result in a hyperplane, right. So for example, if you have a collection of 2 orthogonal axes, you get a 2-dimensional plane. If you have a collection of 3 orthogonal axes, you get a 3-dimensional plane, and so on. So if you have n collection of n components, you will get an n-dimensional hyperplane, right. Principal component analysis can be computationally heavy, and it kind of uses matrix decomposition techniques in order to fit the model, and it can also include the kernel trick like support vector machines. Right. So it can also use the kernel tricks to identify better principal components, right. So just as an extension of how principal component analysis tries to identify orthogonal axes, right. So let us say you want to transpose this 2-dimensional collection of data points into another 2-dimensional space. The first principal component it will try to identify would be C1 here, the second component would be C2 here, which is sort of perpendicular to C1. Right. So it will try to identify this C2, which will try, and the collection of the C1 and C2 will try to maximize the variance of the data points that you have, right. So it will consider different combinations of C1 and C2 which are perpendicular to each other, and it will choose the combination of C1 and C2 that maximizes the variance of your data points. So how do you practically implement PCA? So from scikit-learn there is a package called decomposition, so a module called decomposition, from which you can import PCA, principal component analysis. One of the important hyperparameters in principal component analysis is the number of components that you want to decompose into. So if you have a 10-dimensional again feature space, you can choose to decompose it into into 2 dimensions, and that's possible. You can also choose 3 dimensions and so on. So the number of dimensions, number of components that we tend to decompose it into is a choice, and is a choice for humans, for us modelers. So if you want to visualize data, then you typically have to restrict yourself to 2 or 3 components here, right. And the way the PCA sort of model works is, so it does not work on the simple fit function. You have to do a fit transform function of all your features, right. And then the sort of recovered features or your actual features you get using this inverse transform function, right. So the set of decomposed features you get from this fit transform. So these are the set of orthogonal axes or orthogonal features that you get from your PCA, and if you have a set of decomposed axes, you can also do this inverse transform, and then you can recover back your original set of features, right. So in principal component analysis, your objective is to identify the set of orthogonal axes that maximize variance of your data. So that is on projection learning. The other way to do dimensionality reduction is what is referred to as manifold learning, right. So what is manifold learning, right. So here we try to recover the lower dimensionality of a data set that has actually been rolled into a higher dimensional manifold. The classic example is a kati roll or a paneer roll, right. So there you take a chapati or roti, you put some stuffing on it, and then you roll the chapati, right. So chapati is a 2-dimensional object, but once you roll the chapati and get a paneer roll or a kati roll, you get a 3-dimensional object, right. You get a cylindrical object in a cylinder which has been wrapped, right. So you basically from a simpler 2-dimensional object, if you roll it, you get a more complicated 3-dimensional object, right. So the rolling process is easy, but the unrolling process is not straightforward. So let us say you were presented with this collection of data points, right. So yellow is one kind of data, orange is another kind of data, and then you have red and then brown and so on, right. Unrolling this is not a straightforward process, right, and the models that do manifold learning or try to learn these manifolds try to unroll this as efficiently as possible, right. So and in sort of manifold learning, simple projections do not generally work, right. So let us say I take a projection of all of the data points that I have here on my x1 x2 plane here, right. So for each of the data points I just take the projection values, and if I were to plot it, I see that all of my data points are fairly mixed, right. So I cannot use this for any classification, or even for regression tasks this may not be a very straightforward way to use. So simple projections do not work, but if I were to unroll this carefully, right, then I can get a clear distribution of data points that sort of looks like this, right. So Z1 represents my unrolling sort of feature or axis, right. So if I were to do this more carefully, I can get a clear separation of yellow data points versus orange, red and brown and so on, right. So in manifold learning, whatever higher dimensional rolled data set we have, we try to unroll it and get a representation in a lower dimensional space. So how do we do this in practice, right. So one of the most popular models for manifold learning is what is referred to as locally linear embedding or LLE, right. So what this manifold learning model does is that it tries to relate each instance to its nearest k neighbors, right. So for each data point, it tries to identify its nearest neighbors and tries to have a relationship or a distance metric or something like that, similarity metric between neighbors. And once it identifies similar looking neighbors, it then tries to look for a lower dimensional representation of such neighboring data points while preserving their neighborhood itself, right. So for k sets of neighbors, so let us say 5 neighbors, it tries to preserve the neighboring it tries to preserve the set of neighbors for a given data point. So 5 neighbors for a given data point, for example, and it tries to look for a lower dimensional representation which preserves this neighborhood, right. So that is what manifold learning does, and in general manifold learning can be very slow compared to projection techniques, right. So in projection techniques you are trying to construct orthogonal axes or hyperplanes, right. Here you are trying to preserve the local neighborhood or local similarity of a set of data points, right. So this is often slower. But in scikit-learn you can straight away implement locally linear embedding or LLE models from this manifold module. There are 2 important hyperparameters in LLE. So one is the number of components that you want to project into. So this is the dimensional space that you want to get as your final output, right. So in general, if you are looking for visualization exercises again, so if you just want to visualize your data, the number of components here should be either 2 or 3. The number of neighbors basically refers to the neighborhood itself. So if you give a value of 10, for each data point it will try to preserve its 10 nearest neighbors, right. So once you create an instance, you can then do a fit transform again similar to your PCA to get the set of decomposed features, the final set of features. There are also other dimensionality reduction techniques out there which are more powerful than PCA and LLE. I am just listing them. I mean I am not going to go into the details very much, but the popular ones are random projections, where you try to use some kind of random linear projections here. Multi-dimensional scaling, it tries to preserve distances, so it uses a distance metric as a similarity metric here. Isomap sort of represents all the data points into graphs, and then it tries to reduce distances on those on that graph representation. TSNE or T distributed stochastic neighbor embedding is a very powerful dimensionality reduction technique, and it basically defines a similarity metric between instances and tries to cluster instances that are similar together in a lower dimensional space. And you also have LDA, which is linear discriminant analysis. So all of these models are fairly powerful. They have their own individual strengths and weaknesses, and they are all available to be implemented quite readily, right. But these are good dimensionality reduction techniques to be kept in mind. So with that, we will summarize this lecture, where we looked at both ensemble methods and also dimensionality reduction techniques. Keep in mind that ensemble methods can be used for both classification and regression tasks. It turns independent, diverse and weak learners to create a fairly strong learner which takes in aggregated outputs. We also came across bagging and pasting. So bagging is sampling of data points with replacement, pasting is without replacement. Boosting and stacking, so boosting is a way to do sequential learning instead of simultaneous learning. Stacking is a way to make the models even more powerful by learning the aggregation part as well, in addition to just instead of doing simple mean level aggregations or majority votings. And we also saw that ensemble methods can be computationally quite heavy compared to simpler models. Right, and we took a deeper dive into random forests. We looked at gradient boosting and adder boosting as examples of sequential learning as well. And then within dimensionality reduction, we touched upon the curse of dimensionality, how data tends to spread out, becomes sparse under high dimensional spaces, and we also looked at projection and manifold learning as ways to reduce the dimensionality to get rid of useless features. One of the popular models for projection learning is PCA, or principal component analysis, and one of the popular models for manifold learning is LLE, or locally linear embedding. And we also looked at some hyperparameters for these dimensionality reduction problems, such as number of components, number of neighbors, and so on. I am also including a slide on that summarizes important functions or classes that we discussed in this lecture. So in the next lecture, we will be looking at neural networks and more advanced and complex machine learning models. So with that, I thank you all for joining today. I will see you all in the next lecture.